Right, I will record this as well, and I am streaming it in Teams. Right, breadth first and depth first search or traverse, two really important algorithms that allow us to just like walk a graph structure. Okay, now remember that when we're talking about graphs is a base structure that other things use. So a tree, remember, is a form of graph. Okay, so if we can use this for a graph, we can use this for a tree as well. All right, and you may get asked for either in the exam. What's really nice about these two algorithms is they're essentially the same algorithm, but they use two data structures that we've met, the queue and the stack. Okay, depending on which data structure you use to organize your nodes will depend whether you're doing a breadth first or a depth first search. Okay, now I've put in brackets traverse, and this is really, really important. If you're traversing a structure, that means you visit all nodes. So you may get asked in a question to traverse. What they'll want is a list of the nodes in the order that you visited to show that you've followed the algorithm correctly. If they say search, well, you're going to follow the same process, but there is one big caveat. You stop when you find the node you were looking for, but you use that traversal method. If you don't find the node, obviously you end up visiting all the nodes. Okay, so it's really, really important because they will switch that around. You'll get plenty of indicators. They will use the term traversal search, but actually if they tell you that you're looking for a particular node, you know you're doing a search. Okay, so you've got to be really careful. I've just marked the final the final exam that we've done with Year 13, and there was quite a few instances of people not reading the bloody question. All right, so it's really, really, really important that what you do is that your foremost action is always to just double check what have I been asked to do. Because with a lot of the topics in computer science, you can really go off on one if you miss one particular keyword. Okay, so always double check. Am I just visiting all the nodes or am I looking for a particular node? Okay. Right, so let's have a look at, I'm going to look at both of them, but we're going to start with breadth first search. So let's give ourselves a little graph. And the key to practicing these is to just create yourself lots of little graphs and just have a go at doing them. Right, so let's make just a little graph. So I'm not going to put circles around it because I can't be bothered. Yeah. Is it not? His team's not sharing it. Log out and log back in because I am sharing my screen. But it says there at the bottom as well. Yeah, that's why I just said log out and log back in. I didn't create SharePoint. I didn't create Microsoft Teams. I didn't create any of these bits of software. So we're beholden to the infrastructure company, Microsoft. Okay, so if there's an issue with it, it'll likely be them, and I can't really solve it.
So why don't you stop sharing and reshare? Can't you rejoin it still the same?
It's still the same. Well, I can try, but I am recording it, so because I don't trust any of this stuff to work ever. The fact that you can't get a little preview of what you're sending out. No, is it there? Useless. Right, okay, so let's just create a simple graph. The letters are meaningless, they're just markers to identify the different nodes. Now, you'll notice straight away there's going to be a problem here, and I don't think the exam board have really thought about this too well. I've started doing Well, I've started doing a certain thing, and I'll explain it when we go through this. Right, so there's a little graph. This is what we will call an undirected graph, because I have no directional information. You can travel from A to B or B to A, so that makes it undirected. If I start putting restrictions, you would see something, maybe arrows or something, to say I can only travel from A to B, I can't go back the other way. In general, we're dealing with undirected graphs. As it's a graph, there is no start point until we say a particular node is a starting point. But we do need, if we're going to traverse a structure, we do need a start point. So we're just going to pick one arbitrarily, and I'm going to pick B as my start node. So that's going to be my start node. But I could start from any node in the entire structure. Okay? And I will produce a different traversal. Right, so we're going to do first breadth first. So all you need to remember for breadth first, what does breadth mean? Yeah, it's that, isn't it? It's that. Okay? Which is different to depth, because depth is that. So in your head, remember, right, okay, breadth is what I would call a layered system. So layers, onion rings, if you had a circular structure. Okay, so this is layer by layer. The structure it uses, the data structure it uses, is a queue. It is the queue system that provides us with this layer by layer approach. Okay, so this is the process. We add the start node to the queue. So we know about queues. Okay, they're simple structures. They make you process things in the order that they were added. That's what a queue's for. So if we just draw a little queue, it's got to have enough space for all the nodes. So we've got 1, 2, 3, 4, 5, 6, 9. So I'll just make it, that looks big enough. So I'm just going to draw myself a little queue. Right, so we select the start node, and what we do is we just on queue. So we add that to the queue. Now I don't need to keep track of front and rear pointers because I can see where the front and rear is. All right, so I add B to the queue. That's this thing that starts it off. What we now do is we do a loop. So this sounds a little bit like what Dijkstra does. Remember, Dijkstra was keep processing things while we have things to process, and then stop when there's nothing left. So what this algorithm does is it says, while there is something in the queue, carry out the search process. So we put something in the queue to make sure it starts. Okay? So all we do is we take the first item out of the queue. So we're not going to scrub it out or delete it. I'm just going to put a marker next to it. And I'm doing it underneath. Okay, so I can see that I've now removed that. When I remove something, I examine neighbours. And I go, okay, what are the neighbours of B? So I look at my little graph and I go, right, okay, neighbours are A, J, and D. Okay? So I need to add these to the queue, but how do I know what order to add them? Anybody guess what order I would add them? Lengthwise. What if I gave you the diagram and you were looking at it from across the table? Say we were working on it as a group. Where would left be? So you can't, the notions of left and right don't make sense on a graph, because actually I could have just drawn it differently, couldn't I? So there is no notional order with neighbours. So for me, and what I will ask you to do every single time, is I'm going to tell you to do it alphabetically. so that when we're working on solutions and we're like trying to say, have we got this right, we can look at it easier. There is no defined order. The key bit is the next layer you would visit. Okay? It's all about the layering. But to make it easier for us, if we just say, right, we'll add them alphabetically. So if I'm going to add these alphabetically, I'm going to add to the queue an A, followed by a D, followed by a G. J. G. Right, I need to also keep track of the order that I've visited these nodes. So I said I've just selected B from the queue, so I'm going to put that down as visited. Okay, so this is the visited order. So I've got B. And I've added 3 more things to the queue, and that's all I do. All I've got to do is keep taking the first thing off the queue, add its neighbours. But there is a caveat. So I'm going to go for the next. So that's one loop. So it's just, my neighbours. So it's actually really a simple algorithm. So I'm going to take A off. So I'm going to write that down as visited, and I'm going to look at my neighbours. So I can see I've got F, C, and B. Now I could put B back on, but I'd end up with an infinite loop. Because I'd find B again, and then I'd add A, G, D. And they would appear multiple times. We're not interested in that. We're visiting the nodes once. Okay? So if we've got something in the visited list, we don't re-add it to the queue. So when I look at this, I go B, oh, that's been visited. Don't put that in there. C is my neighbour. So I'm going to add that to the queue, and F is my neighbour. So can you see how we're building up this queue? And actually the queue is doing the layering for me. Right, so I've done B and A. So I now take the next thing off the queue. So I'm just doing the loop again. So that's the process, and we just keep going. So I take D off, so I write that down as visited. Now, D's over the other side of the diagram, and I look at my neighbours. So B, no, I'm not going to put B on because it's been visited. But I have got M and K. Now, assuming you have the power of the alphabet, and you know which one comes first, if you're like me, you might have to do the little rhyme that does the alphabet for you in order, because you can't remember these sort of things. So I would have to do, I'm not going to do it, but I in my head I have to do the song for the alphabet. Not the Sesame Street version, okay, to know that K is first. So I'm going to add K, then M. Okay. Right. And that's it. I've added my neighbours. I haven't got to do anything else. I just start the next process, which is, oh, there is something in the queue. Let's get it. So the next one is J. J has got one neighbour, B, but it's already been visited, so there is nothing to add. So we haven't increased the queue size this time. So I then go, right, okay, let's carry on processing. So we get C from the queue. Look at C's neighbours, got an A as a neighbour, but that's been visited, so we're not going to add that. And it's got H. Ooh, H is a new one, so let's add that to the queue. And then we carry on. So we go, okay, remove F. F's got one neighbour, A, but that's already been visited, so there's nothing to do. Let's remove the next thing, K. Once you get to the extents of the tree, you won't be adding things on. So we write down K as visited. K's got just a neighbour D, but we've already visited D, so nothing to do. Take the next thing from the queue, M. M's only got a neighbour D, which has been visited, so nothing to do. Take the next thing from the queue. So we've just emptied the queue. If H has no neighbours to add, then we will finish the search. And that is true. C's already been visited. Okay, so when this is marked, they will be looking for the leveling. So they'll assume you got B first, then the next level was A, D, J. The next level was actually all of the other ones. So the order in the exam, they cannot, unless they draw their graph in a certain way and tell you to go left to right or alphabetically, they will expect just the leveling. Okay? If I'd have had another level of depth from B, then the levels would have been different. That's the process. Now, what I want you to do is I want you to do the... Yes, Dan? Oh, yeah, right. Yeah, that is a fourth layer. So that's what they would mark. You would get a mark for getting each layer correct. Okay? Now, I want you to do the exact same process, but instead of a queue, I want you to use a stack. Alright, so have a go at doing the same process, but this time, use the same graph, start at B, but create a stack instead. When you do this, remember, stacks are a bit trickier to draw out than a queue. So when you're doing a stack, do it like this. When you remove something, do that, start a new stack. And then let's say you were adding the next things, whatever they are, Z, K, M. That's fine. When you then need to remove the top of the stack, which is going to be M, redraw the stack. And then you can show the development of the stack. Alright, so have a go at the exact same... Oh, that's so annoying. Just do it alphabetically again. You're going to... Yeah, so you're going to push to the stack alphabetically. So when you do this one, it's going to be A, D, J. So J will be at the top of the stack. So that will be the one that gets processed first. No, it's all in one stack. You're only drawing a new one to show the clarity. Otherwise you'll have crossing outs and it gets a mess. Right, so there are only 3 steps. If we want to think at a quite abstract level of implementation, there are only 3 steps. Push the start node, then the loop is pop the stack, write it down, mark it as visited, whatever you want to call that, and then push its neighbours on the stack if they haven't been visited. That's it. And then go back round and do it all again. And then you stop if there's nothing on the stack. Okay, so I'm going to draw myself a stack and I'm going to put my B in it. Okay, so I pop the stack. So I always tend to do this just to be super clear about things. Right, so I've popped it and I'm looking at the neighbours. So I've got A, J and D. So I'm going to put them on alphabetically. So I'm going to put A, D, J. So J's at the top. Okay, so the largest alphabetical is at the top. Again, in a question, they may say the order doesn't matter, but they're more likely to ask you to do a depth first traversal of a tree. Okay, because then the order is implicit in left and right. Okay, so I've done that step 3. All I've got to do now is say, right, well, I've got to keep going now, and I just keep popping things off the stack and adding neighbours if I can. So I pop the J. Now, the reason I also write this like this is because I've forgotten to write them down. But I can quickly look back and go, oh right, look, it was B, then it was J. Okay, so I'm like double checking, I'm validating my own work. Right, so my neighbours of J. Well, actually, that's an interesting one because it's only got B as a neighbour, and that's already been visited. So there's nothing more to put on the stack. So I'm just redrawing the stack so it's nice and clean. And I can see I'm going to pop a D. Right, D's got some more interesting neighbours. B, we've already visited, so we're not going to add that. But I have got K and M. Again, K comes before M, so M's the last one we put on. Right, I'm going to pop the top of the stack. So I take my M off. I look at what's neighbouring M, it's only D. We visited that, so there is no more to put on the stack at this time. I'm going to pop the next thing off the stack. Oh, it's a K. K has only got a neighbour D. We've already visited that, so that's no shakes. So what you can see we've done so far, we've explored one full extent of this graph. We have got the A branch. So all the other nodes have been visited. We've now got the A one to do in its entirety. There's no layer in here, it's a depth search. Right, so we pop A, which leaves us with an empty stack, but luckily we've got some neighbours to put on, so we haven't finished. Right, we have got F and C. So C, we're going to push first, then F. Then we're going to pop, and we pop the F. We look, and we redraw that stack, and we can see we've just got C on it. What neighbours has F got? None. Right, so there's nothing to add. It's got A, but we've already visited that. So we pop the stack, get that C. We then go, right, hang on a minute. There is a neighbour there, H. We then pop the stack. We write down H. It has no neighbours that have not been visited previously. So there is nothing to put on the stack, and we end up with an empty stack. So again, they're gonna give you marks in bands. So you will probably get a mark for starting correctly, then a mark for exploring the G branch, then a mark for exploring the D branch, which was those three, then a mark for exploring the A branch, and then H on its own because that was part of the little C branch. So can you see we explore a branch fully? Depending on what you're trying to do with your graph structure will determine which algorithm you want to do. If you want to know what the next, let's say you were using a graph to store moves in a game from a given position, you might use depth first to see what's my next possible move and what's the next one down. Okay, so if you was to use, you wanted to know what is, if I pick the next move, what's the end game? Where can I get to? You might use a depth first search to go searching all the way down and saying, where does this end up? Okay, if you want to know what potential options have I got for the next two moves, you might use a breadth first search, because that would say, right, okay, go down, two moves. The game of chess is usually stored in some sort of tree structure. Well, not a binary tree, a multi-branch tree, a graph. And you would use these graph searches to work out what possible moves you can make. Okay? Brute forcing chess algorithms, which becomes super time consuming. You can't actually do it because the number of moves, it's exponential. And the search becomes humongous. More search positions than there are atoms in the universe or something stupid. That's to do with random probabilities, isn't it? Yeah. It's interesting, all that sort of stuff, because you can use it. Right, okay, so for me, the algorithm to remember is this. These three steps. Put your starting node on your data structure, whether that's a stack or a queue, depends on which search you're doing. And then just keep processing that data structure. If it's a stack, we pop and push on neighbours. If it's a queue, we dequeue and unqueue neighbours. That's it. It's the same process. But you can get two wildly different outcomes. We can use these things when we're doing maze generators and maze solvers. So we use these depth first and breadth first a lot of the time. They're really core algorithms in computer science. Okay? Navigating systems that you don't know. You don't know where you're going to go from a certain position. You've got A star and Dijkstra if you know where you're going to go to. If you're searching for a particular goal, they're great for that. But these are more general algorithms. And you can see, you can look at these and you can see a little bit of Dijkstra and A star in the process. There's a similarity. Okay? Right, I'll stop the vid there.